Okay, thank you very much, Pierre Guy, and thank you very much, Daniel, for the invitation to organize to allow me to talk in such a nice conference. I would prefer to give this talk lively, right? I mean, in front of all of you, preferably in Paris. But I mean, since we are in this different situation now, I'm more than happy to provide this talk online to you. So I already said to Pierre that he can interrupt me at any time, right? So let us try to make this talk the more dynamical, the better. So I'm going to share my screen now, and I assume that all of you see it, okay? Can you confirm, Pierre, that you are seeing?
I only see a blank screen. I was seeing a nice PDF, and now I don't see it anymore.
That is
Yes,
weird.
now I see it again.
Let me try it again. Full screen mode. No, it becomes.
No, it's blank.
Yeah. So what would you prefer? Can I present like this?
I think it's fine like this. No, it's fine like this. I think.
Okay. Okay. So today I invite you to discover a little bit about a recent area of mathematics that's called dynamical systems. So I'm going to try actually to give a kind of a historical introduction so that we can better understand what is the origin of this area. This will be mainly the part one of the talk, as you see here, historic introduction. And in the second part, I'm going to try to show to you how this area is nowadays studied. Actually, I'm going to give a very simple example, but yet very beautiful example of a theorem in the area of dynamical systems, which is called Sharkovsky theorem. Okay, so let us start from the beginning, from the historic introduction. And in the historic introduction, I will go far in the past. So I want to discuss to you about astronomy in old times. In the sense, I mean, what was our interest or the interest of the society to look at the sky and to try to predict the movement of planets and stars and so on. Well, of course, we all know that this has a kind of a romantic reason, right? When two people are in love, they like to look at the moon and to say some poetries and so on. But I want to focus on the more practical question and ask how does the movement of these planets and asteroids in the space, in the sky, influence the life around us here? Well, perhaps one of the first things that the society realize about the influence of these planets in our daily basis is related to the stations, like spring, summer, fall, and winter. And this was actually very important to when the society started to organize in big groups. For instance, you can see here a piece of stone. This is from the reign of a pharaoh called Thutmose III. It's from 1400 before Christ. It's actually in the Louvre. And this stone, you have some inscriptions, which is a kind of a calendar of the festivals that were organized during the year of this pharaoh. And the festivals were somehow related to the weather. It was somehow related to the seasons around the year, because if you want to make some festival related to harvesting, you have to do it in a time when harvesting is good. If you want to do a festival, for instance, to worship the sun, it is better to do it in a period in which you have more sun, so it would be better in the northern hemisphere to do it, for instance, in June, July, and August, and so on. So it is actually quite old that the humanity realized that the positions of the stars, they have associations with the seasons that we live here in planet Earth. And by that, you can organize better in order to do, for instance, the festivals. And this is the motivation that I put this picture here for you. Okay, you can better organize calendars if you understand the movement of some stars in the sky. And well, this was not only related to parties, to festivities, but it was also related to the growth of the population. And when you have a population that grows, you need to feed this population better. So it also has influence, and this was observed in old times, that the positions of the stars, if you understand them, you can make an improvement in the agriculture. For instance, you can make the plantation, start the plantation in a time in which you have more rain, or the necessary quantity of rain, so that the seed can grow in a better way, and then you can harvest the fruits or the products in a better moment as well. So this is a picture also from the Egyptians, which shows them harvesting wheat. Okay, and the Egyptians, they already knew as well that the movement of planets could give them indication of the seasons during the year, and by this indication and by this knowledge, they could better organize their agriculture. Well, these are two examples which are in some sense you take into account the whole year in order to do these predictions, to do these organizations. But we can ask ourselves if this understanding also has some practical use for our daily basis, like during one day. Can we benefit from the movement of the planets in the sky to our quality of life in some sense? And the answer is also yes, because, for instance, people understood that the movement of the sun around the day, it can give you an idea of which part of the day you are. For instance, we know that when the sun is right on top of our head, it means that we already had half of the time of sunlight of this day. And this would be very good, for example, if you were working in the agriculture and you need to make a break in order to have lunch. So by applying the sun watch, and what is the sun watch? It's just a piece of a stone, a plain stone, and then you have this stick here, and depending on the position of the sun, you have a shadow in this piece of a stone, and the shadow gives you an idea of what time of the day you are. So again, by the movement of this asteroid, which is the sun, you can gather knowledge about your day, and by that you can make better choices during your day. Okay, well, I'm actually going to give you a fourth example of how astronomy was important even in old times, but not so old, and this is related to the creation of maps. So if you belong to a group of people who at old times wanted to extend their border, or just wanted to make a better of the trade between countries, it was important to understand what were the better ways of going from point A to point B. And by that, you needed to represent the world in some way, in some plain way, using maps. And well, it was also observed that maps could be made, or could have the aid of the positions of the stars in the sky, so that you could have more accurate maps. And here is an example which I believe I chose. It's related to the navigations that happened in the mostly in the centuries 15 and 16. For instance, in one of these navigations, it was when the Spanish came to the American continent and they discovered the American continent. And right after, the Portuguese discovered the Brazilian country, which is the one that I am originally, and I am speaking to you actually from Brazil right now. Okay, so the improvement of maps was also possible as you got a better understanding of the positions of the stars, and the more accurate you understood the position of the stars, the more accurate you could do the maps, and the more accurate you could go from one place to the other. Okay, so because of all these questions, which are actually important for the societies in which these questions were made, and they are somehow important to us up to nowadays, you could try to understand how to predict better the movement of the planets. Because if you want to, for instance, organize a trip, a navigation going from, let's say, Portugal to India, you wanted to know in advance what were the positions of the planet so that you could draw the better route for you to follow. So the question now is not only looking at the sky and seeing where the planets are, but looking at the sky and seeing where the planets are, and furthermore, trying to predict where the planets are going. Because depending on the movement of the planets, you can better localize yourself here in the Earth. And by that, I mean that how can we create a model for the universe? So the natural question, if you want to go further in trying to give better predictions, is to try to create a model, and here I mean a mathematical model, in which this model, it reflects very well the observations that you are making here in the Earth, and also as time goes by and you make more observations, these observations were actually predicted by the model. And the better the predictions are confirmed, this means that the better the model you chose in the beginning was made. Okay, so the development of models for the universe, it follows actually the quality of equipments that you have. Because if in the past you didn't have good equipments, you did not make good observations, so more or less any model could work. But as time goes by and you have better equipment, you make more finer predictions, and you need actually finer predictions in order to improve the route of a navigation or other things. And for that, you need better models that give you these better predictions. Okay, so we are now going to discuss some of these models. The first one that I want to discuss is, I don't know if it's the first model that was made for the universe, but I think it's one of the first more important ones. So it's the model that was made by Ptolemy. Ptolemy, I think he was a Greek philosopher slash mathematician slash many other things. And well, to understand the model that Ptolemy created, we have to understand that at that time, everybody believed that we were the center of everything. And if we were the center of everything, nothing more natural than putting the Earth at the center of the universe. So the first conditional paradigm that Ptolemy made was that Earth is the center of the universe. And the second one was with respect to what is the trajectory of what shape do the trajectories of planets and asteroids make. And by that time and up to now, I mean, the most perfect shape that we have is of a circle. So it was very natural to assume that the movements of the planets were exactly around circles. Okay? And if you naively think of these two things, then you come to the conclusion that a good model for the universe is to put Earth at the center and to put all other planets moving around concentric circles, all circles concentric and center, whose center is exactly the Earth. But this model is not good. Why? Because by simple observations, you observe that it's impossible for the model of the universe to be like that. Why? Because if Earth was at the center and all planets were moving in circular circles, all concentric with center at Earth, you would always see the planets when you look at the sky going from one side to the other. For instance, you would always see Venus going from east to west, or you would always see in the other direction, but you would not see some sort of retrograde movements that in a part of the year Venus goes from east to west, and then in another part it goes from west to east. And this is indeed the fact, the situation that you have with many planets. For instance, when you observe Mars and you make a kind of a histogram of the positions that Mars is, you see these kind of retrograde movements of Mars. So here you see in the beginning Mars moving in the picture that I showed to you from east to west, but then at some point during the year it stops moving from east to west and moves from west to east, and then in some time of the year it comes back to moving from east to west again, west to east again, east to west in the picture again. And if all planets were as I said, well, this could not happen. And Ptolemy already knew of these retrograde movements. So what could he propose as a model of the universe that could take into account these retrograde movements? Well, the next picture just show a more accurate histogram of this movement here of Mars. So as you see, in June, Mars moves kind of from east to west, but then towards the end of July until the end of September, it moves from west to east. So the simplest idea that you could have, which was to put everything circular around the Earth, does not work. So what can we do? Well, that's what Ptolemy did. He tried to keep these two ideas, that first, Earth is the center of the universe, of at least our universe, and second, all planets move in circular motions. That he came up with his idea, and his idea is that of epicycles. So he said, okay, it's not possible that planets just move around these fixed circles. But what if I put circles moving around circles? And by that I mean this picture here. So Earth is at the center, but then you have two circles. You have one big circle, which is kind of fixed, and you have one small circle, which is moving. The big circle, which is fixed, is called a deferent, and the smallest one is called an epicycle. And he said, if I put the planet in this small circle called epicycle, and this small circle rotates around the big circle, then the movement of the planet can actually have this kind of retrograde movements. So as you see, here is an example that you start moving this small circle around the big circle in this direction, and then when you see the movement of the planet, which is fixed in this big circle here, but the big circle is moving, then you see from time to time all these retrograde movements here. So most of the time you see a movement in the counterclockwise direction, but from time to time, and I think that this depends on the radii, the ratio of the radii here, and the speed that you are making the movement, you see these retrograde movements. So he said, okay, this seems like a good idea for me to give as a model for the universe. And actually, now I'm going to show to you a video which Pierre is going to play to us, which actually will show to us in a live video that this kind of movement can be obtained if you couple circles inside circles. Yeah, can you tell me when you start playing the video, please?
Oh, sorry, I should have said it's been playing for 20 seconds now.
Oh, why can't I see it?
That's a good question.
Well, but you can all see that as this small circle moves around the big circle, then you see the movement of the planet is just like the one that is depicted here in the picture that I showed to you a few minutes ago. Okay. Well, it's actually interesting that with this idea of coupling circles with circles with circles, uh, you can actually approximate any movement in the plane that you want. So if you are curious, you can go to YouTube now and put epicycle Homer Simpson, in which someone used a program and he coupled many circles, one inside the other, inside the other, inside the other, and the final movement of the planet in the planet fixed in the smaller epicycle is exactly that of Homer Simpson, the shape of Homer Simpson. Okay, I think this is related to Fourier series, but I'm not sure. Okay, so this video was just an example to show to you that with this idea of coupling circles, you could actually mimic the movement of the planets that you see when you look at the sky. Okay, so let us continue here with our slides. Well, but time went by, some centuries went beyond, and people started to realize that Ptolemy's model was not that accurate. Some of the predictions that were supposed to happen based on Ptolemy's assumptions did not actually occur. Or for instance, if you expected Mars to be in some position at the sky in some part of the year, then when you looked at it, you did not see it there. So this meant that the model of Ptolemy, although it was accurate for his time, it was not very accurate as time went by. So the natural question is, what can we do? We either trying to improve his model or we change some of the paradigms that he had. Well, the second model that I want to mention is related to Copernicus. And I think Copernicus is actually already from the 15th century. And Copernicus, he considered the two paradigms that Ptolemy had, and he changed only one of them. He said, okay, I'm going to consider that instead of the Earth being the center of the universe, the center is the sun. So he changed from a geocentric point of view to a heliocentric one. And let us see how we can create a model of the universe still using the idea of epicycles, but just changing the center of the universe to the sun. Let's see how we can create this model. And surprisingly enough, and very good for the astronomers, was the fact that once he changed the center of the university, not the university, of the universe from the Earth to the Sun, he drastically diminished the number of epicycles that he needed. While Ptolemy needed 77 of them, Copernicus only needed 34. And of course, the simpler the model and the better the predictions you can, the more accurate the predictions you can make, well, this is perfect, right? Because you have a simple one which gives you better predictions. So based on that, people started actually to consider the model of Copernicus. Well, I will not go too much in details about the difficulties of the time, but you should take into account that religion was very strong at that time, and saying that the sun was the center of the universe was a big change in the mind of people of the 15th century. All right. So this was the model that Copernicus came with. He improved a little bit Ptolemy's model and got better predictions. So everybody was happy. Well, but time went by. People needed more accurate predictions that Copernicus was not able to give. Copernicus' model was not able to give. So naturally, you try to improve one more time your model. Well, this now was another big change which was made by Kepler. Kepler broke the paradigm that everything was moving in circular movements. Based on his observations, he said that it made much more sense that the trajectories of planets were actually around ellipses. They were ellipsoidal ellipses around the sun. What do I mean around the sun? I mean that the planets move over around ellipses, and these ellipses, one of the focus of the ellipses is the sun, just like in this picture here. Well, Kepler only did that based on his more accurate observations. He and Ptolemy and Copernicus, they did not develop any mathematical motivation for that. So it's quite strange that you should change this kind of perfect shape, which is the shape of circles, to a not so perfect shape, which is the shape of ellipses. So it was fully based on observations that he did that. And fortunately, the estimates, the predictions that he made out of this change were very, very good. So this convinced people that perhaps this was what was actually happening in the universe. Things should be around ellipses and not around the sun, around circles. All right. So this was the improvement, the big improvement that Kepler gave to the history of the models for the universe. Well, nowadays we know, and this came some years after Kepler, that the reasons for movements look like ellipses, you have actually a mathematical / physical reason, and that came with the discovery of Newton of the gravitational forces. So Newton deduced or claimed that whenever you have two masses, you have a force that one causes in the other, and the force is inverse to the square of the distance of these planets, and directly proportional to the masses, to the product of the masses of these two planets. So here is the gravitational force which occurs between Earth and the Moon. Moon, here you should recall that you have actually two forces going on. One force acting at Earth, one force acting at the Moon. These forces, they are kind of attracting in the sense that they are, one is pointing to the other planet. And well, Newton predicted this. He said that this should occur, and based on these gravitational forces, it was more or less possible to show that actually the shapes of the movements were around ellipses and not around circles. All right. As a matter of fact, if for a moment you assume that only, for example, two planets live in the universe, so you only have two gravitational forces occurring, one in each of the planets, well, the shape that they make is actually ellipsoidal in most of the situations. So this was perhaps the first kind of mathematical proof that, based on the assumptions that gravitational forces existed, movements could be around ellipses and not around circles. All right. Okay, guys, if you have questions, I remind you, you can ask during the talk. Okay, so we have a few people here which are trying to select some of the questions, and Pierre is going to ask me these questions along the talk. All right. Okay. Well, this example that I gave to you, that you have actually movements around ellipses, it unfortunately you can only prove this situation if you make this assumption that I told you, that you only have 2 planets in the universe and nothing more. And we all know that we have more than that in our universe. And we have also other things which are not planets. We have stars, and we have some asteroids. And with respect to each of them, there is a gravitational force that acts on the Earth. So actually, well, we know by Newton that movements are caused by forces. So the more forces we have, the more complicated it is to understand what is the final force that acts on our planet. So the harder it is for us to understand what is the direction of the movement and the acceleration that our planet has. And on top of that, as soon as we understand that, and we let time go by, let's say for a year, well, the distances between all of these objects in the universe, they are different. And as you see here, gravitational forces depend on the distance. So the intensity and direction of the gravitational forces acting on Earth, they change. So the speed and the acceleration at Earth and the direction of this movement of Earth, it also changes. So by this, I mean to you that in order to understand the movement, you should take into account that there are many forces going on at the same time. And after any time, after a second, a nanosecond, and so on, the distances, they switch, they change. So you have kind of recalculate what are the new forces and what are the resulting forces and so on. So this is a moving and complex system in which it is not that simple to understand or to try to solve it and then predict what will be the movement of Mars, of Earth inside the universe. And what I just described to you is actually what is called either the problem of the stability of the solar system, or as we in the field call the n-body problem. And the n-body problem is a kind of a simplification of a model of the universe in which you do the following. Consider that the universe is composed of a few bodies, of a few objects. For example, in this example here, you have kind of a universe with five of them. Each of them have their masses, and there are gravitational forces acting for each pair of these objects. So if you have here 5 objects, you have actually 5 choose 2 gravitational forces. 5 choose 2 is 10. Not 10, 5 choose 2. 1, 2, 3, 4. 1, 2, 4, 5. Yeah, it's 10. So you have actually not 10. It's let me do it here. No, you have, yeah, you have 5. You have 2 times 5 choose 2. So you have actually 20 of these forces here, and you have 4 for each of the planets. So each of the planets has 4 gravitational forces acting on it, 1 for each of the other planets. Okay. So the question is, based only on these gravitational forces, can you give me an equation of the movement of the planets, of these 5 bodies? This is perhaps the old way of saying what the n-body problem meant. And the n-body problem, it can be reduced to the stability of the solar system. So if we consider our solar system, in which we have the planets, I no longer know how many planets we have, because by the time I was at school, I think that Pluto was 1 planet, but then they downgraded Pluto and it no longer is a planet. But let's say let's say that you have 9 planets and the Earth. Based on the initial positions and the initial velocities of all these bodies, and based that only the gravitational forces are the forces acting in the system, can you give me an equation of the trajectory that Earth will make in the universe? And furthermore, do these equations, do they imply that the solar system is stable? And here, stability means that no such situation will occur in the future. So for instance, if your model predicts that eventually two planets will collide, just like what the picture is depicting here, then we would say that the solar system is unstable, is not stable. And another situation of instability that could happen was if the planet Earth, for some reason, was ejected from the universe, from our solar system. By being ejected, I mean that the distance of of Earth with respect to all the other bodies could grow arbitrarily to arbitrarily long values. So it was being ejected, and so on. So this would mean, for instance, that we would not have the amount of sunlight that Earth needs. And so this means some sort of instability for our life here. So this question, again, in our context of the solar system, was known as the stability of the solar system, and in a more mathematical way, it's called the n-body problem. Was a question that was raised a few years after Newton came up with his theory of gravitational forces. Why? Well, I think that it's because it was only with the gravitational forces that you could give a reason for the movements of the planets. So a mathematical, more precise model was now possible for us at least to have in mind. Maybe not to prove, but at least to have in mind.
Yuri, there's a question
Sure.
involving the Newton force. It's a question from Rajendra in the audience. Does the Newton force decide the size of the ellipses?
Well, the Newton force is only related to the masses of the planets and to the distance among themselves, right? So if you put two planets far away in the beginning, then the ellipses will be much more stretched. So the sizes of the ellipses will be changed. So the answer is yes. The Newton forces, it changes, but it changes because you change either the masses or the distances between the planets. All right?
Thank you.
Okay. So this question was extremely relevant towards the 19th century, from around the 1800s. And what people at that time actually wanted to do, and this is one of the reasons that mathematics by that time was directed to this, was actually to give us equations by means of either polynomials or series expansions of the movement of the planets. So people by that time wanted to answer the n-body problem by means of precise equations, saying if I have these initial solutions, then the solution to this to the movements of the planets is this. Well, so what they wanted to do, they wanted actually to solve this using that if you see Newton's law by means of ordinary differential equations, what you wanted to do was to get these ordinary differential equations and to solve them and to give the precise answers. This was the question by that time. And this question was actually again raised in a context that I'm going to start to tell you right now. And the context is related to the creation of this journal, which by that time was very new. It was being created. It's called Acta Mathematica. This journal, I should tell you, that is among the top 4 or top 5 journals in pure mathematics nowadays. So if a mathematician publishes in Acta Mathematica, then he is extremely happy. Okay, so it's a very prestigious journal nowadays. In the 1800s, around 1880, it didn't even existed, and it only existed after this guy that's in the picture decided to create it. This guy is called Oscar II. He was a king of Sweden by that time, and he was friends and advised by a mathematician slash physicist, which was called Mittag Leffler. So Mittag Leffler was this mathematician, he was friends with the king of Sweden, and Mittag Leffler suggested to Oscar II to create this new journal in mathematics to try to foster science in Sweden. Oscar II accepted this idea, so he paid for the creation of this new journal, and the journal was created. But furthermore, Mittag Leffler had a good idea to try to advertise this new journal. This new journal was not known by the community, so he needed a way to advertise it. And he came to Oscar II and said, look, your honor, or your highness, I don't know how he was called by that time, is going to be 60 years old in a few years. So we could try to create a prize, and the one who solves this prize, or who gets closer to the solution of the questions that we raised in the prize, will be the winner, and then his solution will be published in one of the editions of Acta Mathematica. This is good because everybody, like highly regarded mathematicians of the time, are going to be aware of the existence of this journal, and we are also going to celebrate your 60th anniversary. So by means of this, Mittag Leffler and Oscar II, they created this prize. So the second picture here is just a print of the cover of one of the first volumes of Acta Mathematica. So as you see here, Mittag Leffler was the editor of this journal. Okay, so right after it was created, he and Oscar II, they created this prize in order to advertise the journal in a better way. So what did the prize consist on? The prize consisted on 4 problems. So each person who wanted to try to win the prize had to write about one of these 4 problems. So you didn't need to write about all of them. You chose one of them, okay? And among the 4 problems, one of them was exactly the stability of the solar system. As a matter of fact, it was just like the one I said. So given the initial positions and the initial velocities and masses of bodies around the plane or on the space, give the exact solution by a series expansion of the movements of the bodies in the system. So it was actually what I can call a quantitative or analytical solution to the n-bar problem. The prize was inaugurated, it was released in 1885, and it was given a deadline of up to 3 years for the applicants to submit their solutions. And after 3 years, the prize had 12 submissions, and one of them was by this French mathematician called Henri Poincaré. So Henri Poincaré was one of the most important mathematicians by that time, and I read some documents talking about the history of this prize, and apparently people knew that Henri Poincaré was interested in this n-body problem. So perhaps one of the reasons that the n-body problem was among the 4 problems of the prize was to try to instigate, to try to make Henri Poincaré to run for the prize. And he indeed submitted a manuscript, but he did not give a solution to the n-bar problem. Instead, he gave a solution only to a special case, and actually only to a special case of the three-body problem, in which you have only three bodies in your system. As I told you, if you have two bodies, the tools by the time were already sufficient to provide you the solution of the two-body problem. So the natural next step was indeed the three-body problem. And Poincaré was not even able to solve the three-body problem. He only gave a solution to a special case. But nevertheless, he got the prize. Why? Well, here is the picture of Henri Poincaré. The reason is that none of the submissions gave solutions to any of the four problems. So Mittag-Leffler, who was the kind of the chief of the prize, he decided to give the prize to that one who gave most contributions towards the solution. And then he gave the prize to Poincaré because, according to the judges, to the referees of the manuscript, they considered that Poincaré was the one who gave more new ideas towards the solution of this problem. Actually, Weierstrass, which was one of the referees of the prize, he wrote to Mittag-Leffler about Poincaré's work, and you can see here that he claims the following: "You may tell your sovereign that this work cannot indeed be considered as furnishing the complete solution of the question proposed, but that it is nevertheless of such importance that its publication will inaugurate a new era in the history of celestial mechanics." So Weierstrass understood that even though the full solution was not given, the ideas that Poincaré gave in the manuscript were very deep, and they could perhaps be applied in other fields of mathematics. And he only mentioned the history of celestial mechanics, but I mean, it's natural that when a new tool comes into play, people start to apply it in many different areas. So based on the opinions of the judges, Poincaré was indeed awarded the prize. His solution was typed, it was printed, everybody was happy, Mittag-Leffler was happy, the Oscar II was happy, Poincaré was happy because he got some money in this prize. So everybody was happy, so end of the story. Well, no. Why? Because a few months after the manuscript was printed, Poincaré found a mistake in his proof. And he actually came to the conclusion that the mistake was not possible to be solved. What do I mean? He could not give a different approach in order to fix this mistake. It was a mistake that was like it would put everything, the whole proof no longer was possible. So what he did, well, he said he contacted Mittag-Leffler and asked Mittag-Leffler to stop printing the volumes that were in print. And Mittag-Leffler said, "Okay, I can print, but we have already printed many. What do we do with them?" Poincaré said, "I buy them all. I'm going to buy everything that you have. Is actually with the price of the money." So he spent the whole price of the money to buy all of these volumes, and apparently he actually paid a little bit more out of his pocket to buy it, so that his mistake would not be advertised in the community, so people will not have the volume with this mistake. It seems that very few volumes have actually survived to the history. I do not know where these volumes are, but I would think that one of them is in the nowadays called Mittag-Leffler Institute in Sweden. But anyhow, Poincaré found this mistake and he started a few months or years to try to fix it, and he was not able to do it. And what was the mistake? He had in his analysis what he called asymptotic surfaces. And he assumed, I don't know why, but it was somehow natural at the time, that these asymptotic surfaces could not intersect each other. And based on that, he gave his solution. But when he realized that he did not have a proof that these asymptotic surfaces could actually intersect, could not intersect, and well, perhaps they did intersect, then he understood that the situation was much more complicated than what he thought in the beginning. And this is the idea that Poincaré's arrow, it led this field of study from stability, which was what he concluded if these asymptotic surfaces did not intersect, to a complete chaos. If there was a non-empty intersection, then they would intersect one to the other in very complicated way, infinitely often, distributed in the position in very complicated ways, just like what this picture here is trying to depict to you. And by means of this presence of chaos, well, then the situation changes. You can no longer tell whether the n-body system is stable, whether the solar system is stable, and so on. And actually, up to nowadays, so this was in the end of the 19th century, up to nowadays, it is an open question to know whether the solar system is stable. Okay, so actually Poincaré's arrow was not influential, influential, but a very deep question, because we still don't know whether the solar system is stable or not. But the discovery of his mistake, it led to the opening of a big list of possible situations in which people thought that everything was stable. Things in nature were supposed to be very stable, because we know that nature tries to minimize these things. So why having chaos in nature? So everybody believed that stability was everywhere. And Poincaré said, no, if this mathematical situation here occurs, then we'll have chaos. And how does that actually appear in some mathematical models? Well, before saying that, I'm going to tell you that this notion of chaos is related to this other notion, which is called sensitivity to initial conditions. And what sensitivity to initial conditions means, I will try to give you by means of a video. So we have the second video that Pierre is now going to present to us.
Okay. Can I ask you some questions from the audience while I'm doing this?
Oh, sure.
There's a question from Sayed Ahora. So can the n-body problem be applied to other real objects in subatomic scales, or any other thing in the universe which are related by forces?
Well, I think it can, but the problem is that even the n-bar problem, I mean, it's not solved. So if you have more forces involved, or forces of other nature which are not related to the distances of the bodies, but only to their how do you call, if they are positive or negative or so on, to other qualities or characteristics of the object, then this perhaps is no longer a simple ordinary differential equation. This can take a much more complicated mathematical form. Okay.
I've just almost started the video. Maybe I can ask another question before,
Sure.
if you agree. A question from Aprameya. Oh, I don't see the full name. I apologize. Aprameya Geersh-Hebar. How did Newton come up with the inverse square law? Was it intuitive or experimental?
I have no idea. People tell about the apple, right? But I don't believe that he was putting the apple at different heights in order to try to guess that. Perhaps he had some like tables of observations of astronomers, and he observed a pattern, or he did some sort of quadratic regression to see that things were related to the inverse of, inverse of the square of the distances. I don't know.
Okay, thank you. So I will start the video now.
Okay.
So we have a front of data initially placed close together on a very tight line, and we evolve it through time on the Lorentz strange attractor. You can already see that this front is being stretched out, and in a moment you're going to see it being torn. This mechanism of stretch and tear is one of the key mechanisms for the creation of chaos, and you're going to see this repeated over and over again on the attractor. In the meantime, I'm going to point out on the middle right, there's a point which doesn't seem to want to go on the upper or lower lobe. This point happens to be very close to something we call an unstable manifold, which is trying to draw it towards a fixed point. If it gets to that fixed point, it'll be stuck there forever. But alas, the point has a happy ending. The unstable manifold is, after all, unstable, and so it won't stay close to it for a very long time, and will evolve back towards the attractor. On the attractor, in the meantime, we've seen a couple of waves of stretch and tear happen. And now, the data points which were once very ordered, now they're starting to appear as if they're kind of becoming random. As these waves of stretch and tear repeat and repeat and repeat, they'll start to appear more and more random. We see two waves now, one on the top face, one on the bottom face, being stretched and torn apart. So as they appear more and more random, it's important to point out that they're not random at all. Chaos is not randomness, which is one of the misconceptions that a lot of people have. So random data has no patterns whatsoever. It's not deterministic. We can't find any structure when we study it very closely. Whereas chaotic data might appear random on face value, but actually behaves deterministic equations. And with enough analysis, we can find interesting patterns and features which...
Yeah, could you play the video again without the audio of the video?
Oh, I'm not sure I can do that.
If not, I mean, I think I'm happy with it, so you can come back to me.
Okay, I'll give you back the rights.
Okay. Thank you.
And you should have them again.
Okay. Okay, guys, so what did you see in the video? You see some picture like this one here. And in this picture here, you saw the movement of many of the particles, which were ruled out by some equations, actually some ordinary, some differential equations. And in the beginning of the video, you saw a bunch of initial particles that were all close together. But as time went by, the positions, the movement that the particles were making were no longer alike one to the other. Each particle was performing the movement in a very different way. So although they were very close together, as time goes by, the positions, the movement changes drastically. And this is the notion of sensitivity to initial conditions. Sensitivity to initial conditions means that you have a system that is in some sort chaotic. And chaotic in the sense that if you change a little bit the initial position that you start with in the system and you let time go by, well, of course, since the initial positions are very close, they will remain close for some time. But as time goes by, after 10 units of time or 100 or 1 zillion units of time, then the movement of the particles will be very distinct one to the other. So the movement is very sensitive to the initial conditions. And this is very important if you want to make predictions, because this tells you that no how to say, no matter how you try to predict what is the current situation of your system, let's say its speed or its position, you are not able to predict it with 100% of certainty. So you're going to have some errors. These are related to the errors that the equipment that you are using have. So if your system is sensitive to initial conditions, then no matter how accurate your equipment is, you're not able to predict the full future movement of this object, because you are going to have mistakes. These mistakes are going to accumulate a long time, and the accumulation a long time is actually going to be arbitrarily large. Okay, so this is among, let's say, non-mathematicians or among general audience, known as the butterfly effect. The butterfly effect, when people try to say, they say something like, if a butterfly moves its wings in Japan, it might change the atmospheric situation in Japan, that nothing will happen in Japan today or tomorrow, but maybe after 20 years, a hurricane will occur in Brazil, which is in the other part of the planet. So the idea is that the butterfly moved its wings, so it changed a little bit, very, very tiny, the initial conditions of the atmosphere, and around time, these initial conditions was accumulating some errors, to the point that after 20 years, a hurricane was created here in Brazil. And this is indeed, if you already saw this movie called The Butterfly Effect, this is exactly what happens in this movie, because the movie tries to depict this effect by saying that small changes in the life of the main character, which is portrayed by Ashton Kutcher, can change drastically his futures. I mean, one of his futures, he is handicapped. In other of his futures, his friend, she is a drug addict, and so on. So this tries in a kind of a literature way to show how the butterfly, what the butterfly effect means. And it actually arose from this idea, or this oversimplification made by Lorentz. Lorentz was a physicist, and he tried to give some simple equations that try to give predictions of the weather, to make the weather forecast. So he came with these 3 differential equations, which are, most of them are linear, with the exception of the last one, which has x times y. Well, but nevertheless, all of them are polynomials, so you would expect to have a concrete solution, to give the solution of this system of equation by means of polynomials or of series expansions. Well, you cannot. He came up that with these very simple equations, even with these very simple equations, the situation can be as complicated as that one depicted in the video. So the idea is that even in simple contexts, chaos can be present. Okay? And how can we then understand chaos? Well, this is exactly what the field of dynamical systems tries to do. The idea of dynamical systems is actually motivated by Poincaré, in which when Poincaré tried to answer the question, he did not answer, but he introduced many new ideas. One of them was, okay, try not to give the description in a very concrete way by means of equations, but try to give a qualitative description. For instance, saying more or less what is the shape of most of the trajectories. So in summary, Poincaré, he changed from a quantitative perspective, which was that of providing the precise equations of the solutions, to a qualitative perspective, which is that of try to give a geometrical or topological description of the set of solutions. So this was taken by this new area which was created by means of Poincaré, and it's called nowadays dynamical systems. So in dynamical systems, we try to give a more qualitative, whatever this means, but I try to explain to you more or less what it means. Qualitative description of mathematical models. Also in models that exhibit some sort of chaos. So even in chaotic models, we try to describe them in a more qualitative way by means of geometry, topology, or even in what you might call a quantitative way, which is from a probabilistic perspective. Okay, but what I mean by no longer quantitative is that we no longer give the precise equations for the solutions of the movements. We try to describe the solutions using other tools. All right. So chaos and sensitivity to initial conditions is actually very popular nowadays. So it is present in many different contexts. One of them, which is the one that I gave to you in the first part of the talk, it relates to celestial mechanics and also to weather forecast. But other ones, and which are actually very simple to explain, you can have some sort of chaoticity in the system. One of them is on mathematical biology, in which you have some colonies of virus, of bacteria, and you want to understand how it grows. So this is called sometimes population dynamics or population biology. You want to understand how the population of this bacteria evolves over time. So you have some examples in which the evolution of this population is in some sense chaotic as well. And chaos also occurs in fluid dynamics, for example. So if you dip water from a fountain, you can have some sort of turbulence that parts of this water cause in the other parts. And well, inside this turbulence, which is related to fluid dynamics, you can also have some chaotic movements. Okay, I believe this was first discovered by David Rouelle, who is a retired professor in France. Okay, so this concludes the first part of my talk, as far as I remember. Yes, so this is a good time to stop, Pierre, and to see if there are more questions about the first part, the historical introduction.
There are, in fact, quite a few questions, if you'd like to answer them.
Sure.
So let's see. So there's a question from Edon Ramadani. Is it possible to give the computer all the instructions like the distances, the masses, etc., and see if it could give us a solution for the n-body problem?
Yes, but the computer also makes small mistakes. Because how does the computer treat real numbers? It treats real numbers by truncation. You have to make some approximations. So because of that, the small mistakes that the computer makes, they can also accumulate on the number of iterations, the number of calculations that the computer has to make, so that predictions in the long time are no longer true.
Thank you. Can you accept another question at this time?
Sure.
So there's a question from Enzo Masto. Can you give us an insight on what new ideas Poincaré introduced in his prize submission, and what are those asymptotic surfaces that you talked about? Can you give us a brief explanation? Cheers from Brazil.
Oh, good. So the asymptotic surfaces, they are what is called in mathematics the alpha limit and the omega limit. Alpha means in the Greek letters like birth, and omega means death. So alpha limit are all accumulation points of the past of the trajectory, and omega limits are all accumulation points of the future of the trajectory. And Poincaré believed that these asymptotic past and asymptotic future, these sets could not intersect. But nowadays we have the idea of homoclinic intersection, which actually gives rise to an idea which was introduced by Ismail of Ismail's, which is nowadays called Ismail's horseshoe, in which this kind of intersection of asymptotic surfaces occurs, and then the dynamical behavior of the system is much more rich, is much richer than if there was no such intersection. Other influential ideas were, I already mentioned, right, to change from this quantitative to this qualitative perspective. And another one that I want to mention, it actually gave birth to a twin area of dynamical systems, which is called ergodic theory. Poincaré, he sketched what is nowadays known as Poincaré recurrence theorem, which tells you that under the preservation of a mass, a finite mass, most points they return arbitrarily close to where they started over time. So if you started with some initial conditions, well, with 100% probability, you will, in some time in the future, you will have almost exactly the same position and almost exactly the same speed that you had in the beginning. So this is the notion of recurrence. It was also introduced by Poincaré, and it gave birth to this area called ergodic theory.
Interesting, thank you. Do you have time for one more, or would you like to wait until the end?
Let me just make you one question now. So
Sure.
how much time do I have to finish the talk?
So the talk should finish at 30, at half past, and then 15 minutes for question.
Okay, so I can accept another question.
Okay, so here's one from Dango Ki. How far in the future can we accurately predict the movement of the planet systems and the chaos effect?
Well, that I cannot answer because I do not work in these experiments that try to make these predictions. My work is pure mathematics. And when you try to answer these questions, you have to know to which extent you are making the your computer is making the approximations, and how many iterations you are going to consider. So unfortunately, I cannot answer that, but I just pointed to you that there are some variables involved in how answering this question.
Thank you very much.
Okay,
there's a lot more questions, but I'll let you continue. Yes.
Okay, yes, because I prefer to finish on time so that we leave more time to the questions that the guys have. Okay, so my goal in this second part of the talk is actually very short. I just want to give you a kind of a taste of what a mathematical theorem in dynamical systems means. And this, I'm going to show to you this by means of this extremely beautiful theorem of Sharkovsky, which has some historical, I can make some historical comments, but as I don't have too much time, I prefer to make the historical comments as I finish the statement of the theorem. I would just mention that it is a theorem from 1965, so it's more or less 50 years old also. Well, in order to explain to you what the theorem is, I should try to give a mathematical formulation of what dynamical systems tries to study. So what is the setup of dynamical systems? Well, I believe you already got convinced that the goal in dynamical systems is to try to understand the behavior of some system as time goes by. Okay, some sort of, you want to understand the evolution of the system. The evolution here is not evolution like we think of humans, but it's just how the system behaves as time goes by. Mathematically, in order to do that, you need two objects. You need the first object, which I call M, which is called the phase space or configuration space, and it is just a set in which all possible initial configurations are there. or all possible configurations of the system are there. For example, if you want to describe the movement of a particle inside an interval, well, the configuration space is you're going to have one parameter to describe the position that you are, and another parameter to describe the speed that you are. So by means of these two parameters, you can describe the configuration of your system. Well, but your system is changing over time. So how does it change over time? Well, then you should also have what is called what I call here the law of evolution, which is just from a mathematical point of view a function that gets a position of space and associates another position of space. So this new position of space, you understand as the position after 1 unit of time went by. So if at position time 0 in the beginning of the movement you are at position x, then at time 1, after 1 unit of time, you are going to be at position f of x. This is just what this function is telling us. And once you have this pair, f and m, then you can rewrite your goal above here, which is try to understand this composition of f with itself many times. You do f, compose with f, compose with f, compose with f, n times. And the idea is to try to understand what this function f to the n is as n goes to infinity. So how does it behave the larger we take n? For instance, it could all converge to the identity map, or it could converge to a map that sends everybody to the same place, and so on. Or it would never converge, it would oscillate among two maps. So this is the kind of questions that we in dynamical systems try to answer. And in order to understand this, perhaps the first thing that you should try to do in order to understand this big map here is to try to understand it by means of periodic points. Because when you have periodic points, well, you know the whole future of the point. For instance, if the point has period 2, so you know the whole future, it only reduces to 2 points, x, f of x, f of x, f of x, and so on. And I'm going to try to make this question in an even simpler situation in which the configuration space is just the interval 0, 1, and we have a function, which is the law, which I call the law of evolution a few minutes ago, and I assume that this function is continuous. Okay, so oversimplificating the question that we want to answer, which is to understand the iterates of this map f, we want to simplify and try to understand by means of periodic points. So the first question is to know whether f has periodic points or no, or a more precise one is to understand what are the periods that appear for this f. Well, I leave as an exercise to you, and this just uses the intermediate value theorem to show that you have one fixed point here. So there is a point x in this interval such that f of x is equal to x. Okay, this is a classical application of the intermediate value theorem, and everybody that made a class in analysis might have seen this. Well, but I want to go beyond just fixed points. I want to understand points of period 2, of period 3, of period 4, and so on. So this is exactly what Sharkovsky gave, and he gave it in a very, very precise way. What he did, he introduced a new order of the natural numbers. So instead of saying 1 smaller than 2, smaller than 3, smaller than 4, and so on, he wrote the natural numbers in a different order, in a way that the larger number in this new order, which I call here Sharkovsky order, is the number 3. And after 3 it comes 5, after 5 it comes 7, and then you order all odd integers, odd natural numbers. 3 bigger than 5, bigger than 7, bigger than 9, and so on. And after you put all these odd integers, you put all twice all odd integers. 2 times 3, 2 times 5, 2 times 7, 2 times 9, and so on. And after that, you put 4 times the odd integers, and so on. And once you list all of these numbers, the only natural numbers that haven't still appeared are the powers of 2. So Sharkovsky ordered the powers of 2 in the usual order, that 2 to the n is bigger than 2 to the n minus 1, is bigger than 2 to the n minus 2, is bigger than 2, and is bigger than 1. So the 1 is just like our natural order, the smallest number in Sharkovsky order, but everything else is different. Okay? So for instance, you can see here by in Sharkovsky order that 14, which is 2 times 7, is bigger than 36, which is 4 times 9. Just because 14 has a power of 2, which is smaller than the power of 2 that appears in 36. Okay? So there are many changes from our natural order of the natural numbers to Sharkovsky order. And why did Sharkovsky put the natural numbers in this so complicated way? Well, because it was based on this order that he proved this beautiful theorem, which is nowadays known as Sharkovsky theorem. What is Sharkovsky theorem? It says the following. If you are in the context that we introduced, and you have two numbers, n and m, in which n is bigger than m in the Sharkovsky order, so whenever f, your map, has a point of period n, the bigger one, then necessarily it has another point of period m. So whatever you see as a periodic point, your map is going to have periodic points of all other periods which appear after this first one in the order of Sharkovsky. For example, if you have a point of period 14 for f, then you also have a point of period 36 for f. It will be another point, but that's what Sharkovsky proved. And one of the strong consequences is that, well, since 3 is the largest number in Sharkovsky order, if you have a point that has period 3, so f to the third power of x is equal to x, then it has another point which has period 5, it has a point which has period 7, it has a point which has period 9, it has points of all periods. So here is the statement. In particular, if f has a point of period 3, then it has points of all periods. And this is just a statement to try to give you a flavor of what is the kind of questions or how we try to understand chaoticity in systems. This is more or less how we dynamicists and people in ergodic theory try to do nowadays in mathematics. And with this beautiful theorem of Sharkovsky, I finished my talk. So thank you very much for all of you to come here and to listen to me for this almost 90 minutes.
Thank you very much, Yuri, for this fascinating talk. I will now call for questions. There's quite a few questions already. So let's see. We have a question here from Srivasta B. What is the difference between instability and chaos?
Oh, well, I think it depends on the person. Actually, none of them is properly defined. And for example, chaos, some people say that chaos is to have periodic points of all periods. So this last theorem would say that period 3 implies chaos. But other people say that chaos is related to have exponential growth of different initial conditions. And this is related to having positive entropy. this notion of entropy. Some people say that chaos is just, let's say, not only to have positive entropy, but to have exponential decay of correlations, which is another concept of trying to understand this instability inside the system. So it's a quite complicated question to try to answer because none of the concepts is properly defined.
Thank you. Here's another question from Dren Zabelli. What kind of mathematics do you need in order to study chaos theory or dynamical systems?
Yeah, this is a nice question because I think that perhaps because dynamical system is a new area compared to other classical areas in mathematics, just like analysis, number theory, and geometry. People in dynamical systems, they usually use many tools. So we use analysis, we need geometry. People who only like this only use this, but there are many interactions of dynamical systems also with other areas such as probability, also number theory, there is interaction, and even combinatorics. So there are some works, influential works of Henri Poincaré from the 70s, which created this bridge between combinatorics and dynamical systems. And after that, there is the work of Grigory Margulis, which he was able to solve a question of number theory using dynamics. This is known as the open high conjecture, and Margulis answered the open high conjecture by means of dynamical tools. Nowadays, there are interactions with geometric group theory. So dynamical system is very nice because you can always find some line of some direction that you like inside dynamical systems. So people who like the number theory can go to that number theory. People who like combinatorics can go geometry, analysis, probability, and so on. So I would say that the tools are everywhere. So the first thing is to do a good undergraduate, a good master's, and then try to do dynamical systems and ergodic theory in the PhD.
That's very, very, very interesting. Another question from Robert Murphy. Is the study of unstable systems useful for describing black holes?
I don't know, because I know nothing about physics. So nowadays, one of the ways of saying that the system is unstable is exactly saying what Poincaré said. You have asymptotic surfaces that intersect. This nowadays is known as an homoclinic intersection. So if for some reason, some people that know more than I do know that in the models related to black holes, you have these homoclinic intersections, then dynamics is useful in order to understand it.
There's another physics-related answer, an astronomy-related question. I'm sorry. What is the sorry? It's a question from Raymond Drira. What is the impact of an expanding universe on the solar system stability?
Again, I know nothing about physics, so I would not know how to answer that. Let me just mention that Poincaré. I mentioned Poincaré's recurrence theorem. And Poincaré recurrence theorem, he considers that you have preservation of volume. So the space in which your object can be, it has the same volume all the time. So I would assume that in an expanding universe, this would be violated. So you would need another field of dynamical systems in which you have no preservation of volume. Okay, but there is one part. Unfortunately, it's very abstract. There is a part of abstract ergodic theory, which is called infinite ergodic theory, that allows you to have infinite volume, and that things do not get preserved as time goes by. So this is perhaps one of the ways of going towards this question from an abstract point of view.
Thank you. A historical question now from Matvey Tsiryanov. How developed is the theory of dynamical systems in our days compared to in the 19th or 20th century?
It's pretty much developed, but for people like me who work in the field, we know that there are many more questions to be answered. Okay, so it is very surprising that this field evolved so fast and interacted with so many areas. I could continue going on here on the list, so you can talk about C-star algebras, which is another field which is somehow more abstract, that is also related to mathematics. So you have all the abstract points of view of dynamics that you can get involved with from a dynamical point of view. So it is very developed. It is still developing very fast, to the point that every time the Fields Medal is granted for, I would say, the last 30 years, there is at least one person in dynamics among the 4 awardees. So it's a field that people are putting a lot of effort to go beyond, but still there is a lot to try to understand.
Which is probably why people are putting in a lot of effort.
Exactly.
Another question now about applications from Yves Lecomte. Can dynamical systems and the chaos theory be applied to non-physical problems, such as the understanding and prediction of financial markets?
Yes. Yes, there are some people who try to use this perspective in dynamics. Some of them use, well, it depends on the paradigm that you have for the market. Some people say that the market is not deterministic, so it's purely probabilistic. So then it's better for you to use probabilistic tools. Some people say that it is deterministic, and they try to model from this point of view. So you have to look at the data that you have and try to just like Ptolemy did, to concept a model that better shows is related to this data that you already have, and can predict and can go directly on the precise predictions that your model is giving you. So the whole idea is look at the past, see the features of the past, come up with a model that tries to predict the future in a reasonable way. So from a deterministic point of view, you can use dynamical systems to do that. But you can also do from a deterministic point of view that also has some randomness in it. Some people study dynamics from this point of view. You have a deterministic plus a small mistake every time you apply your system. A kind of white noise, which we call white noise, okay? They are called slow fast systems and so on. So they have been studied very much in the last 15 years.
It's really a lot of applications.
Yeah.
There's now a question from Sunny Zhang. Interesting. Could you please give us some hints for the proof of Sharkovsky's theorem? Like what ideas are used?
The only tool that you need, mathematical tool, is the intermediate value theorem. That tells you that if you have a continuous function that assumes the value a and b, then it assumes every value in between a and b. But you have to be clever on how to apply this. One of the ways is actually a solution to the question that I left you, to show that you have a fixed point. How do you show that you have a fixed point? You only need to find an interval in which the image of the interval contains it. If image of the interval is contained in the interval. And as I assumed that the function goes from 0, 1 to 0, 1, the image of this interval 0, 1 is contained in 0, 1. So this guarantees to you the existence of a fixed point. If you need a periodic point, then you need an interval that after n iterates, it's contained inside itself. So in order to find these such intervals, then it's where the assumption of the point of period 3 comes up. Point of period 3 tells you that you have a point P that goes to f of P, that goes to f square of P, that comes back to P. And by these 3 points, you can define 2 intervals. And it's very easy to see what is the relation of these 2 intervals with respect to their images. So the image of one contains the other, the image of the other contains both of them. So you have a sort of a graph which has 2 vertices, and we have a loop here and an edge come to this one, and you have an edge come to this one back. And this graph, it has paths of any length because it has a loop. So the idea is to explore the loop, create this path of length n, and because this path has length n, it translates back to having a point of period n. Okay? This is the proof of the easy part of the theorem, in particular if f has a period 3 and so on. For the more precise one, which is actually the one that was proved by Sharkovsky of the order, then you have to better understand what the assumption gives you in terms of these intervals and the graph that you have associated to it, and what are the sizes of the loops of the closed paths that you will have in this graph. So this is the idea. Okay. There is a nice paper of Keith Burns and a co-author that I forgot the name, in which he gives a full proof of this. It's a paper from 2007 and so on. So everybody can take a look at it and understand it.
It's not every day that you need so little tools in order to prove such an important theorem.
Yes. It's elementary, but clever.
Yes, I assume so.
Yeah.
Another question from Kwang An Trin. Is there any case where the system becomes chaotic, but then after some time reverts to order?
Yes. You could have this depending on what the notion of chaoticity you have. Again, coming back to the notion of chaoticity. For example, if chaoticity for you means positive entropy, then I would say that the answer is no. Because if an iterate has positive entropy, then all iterates will have positive entropy. Okay, this is a result in the field. But if you say chaoticity just by meaning that the initial positions are far away, that the current positions are far away from the initial positions, then you can have a situation in which everybody starts in a position, then after some time it's in unrelated positions, but after some more time come back very close to where all of them started in the beginning. So if your notion of chaos is weak as this one, then the situation can go to chaoticity and reverse back to kind of order. So it all depends on your concept of chaos.
Yes, your definition has to allow for this to happen, I guess.
Yeah.
If you still have time, we have more questions.
I have time.
So a question now from Stefan Pajaniadia. It's a historical question, was there opposition to Cair's theory in the mathematical community?
Wow, that's a good question. I never thought about it. I would not know, but it developed so fast that maybe it didn't have time for opposition. And in mathematics, if you prove something, people do not oppose to it, right? I mean, I think that opposition is, you cannot oppose to a correct proof. So after Poincaré came with this idea, some other ideas were developed a few years later by Hadamard. And well, it's nice, right? Because Fondation Hadamard is one of the organizers. So Hadamard in 1898, he came with some ideas to try to understand geodesic flows, and it was a kind of it had a dynamical systems perspective. And after that, I mean, people started to dig into many contexts, and all of the proofs were correct. So there was no opposition for that.
Yes, it makes sense. Thank you. Here's a question now, a bibliographical question from Enzo Mastro. What are some introductory resources that one can use to learn about dynamical systems?
So it depends on your level of interest. For example, if you just want to know what it is, a little bit more than what I explained here, there is a movie which was made by Etienne Gis. I think it's available online, and it's a very interesting one. It shows many examples in which kind of chaos comes up. I really recommend it. Whenever I have students that start getting interested in dynamical systems, I recommend them to take a look at this movie. Okay, if you want more like written literature, then you have a bunch, many books. You can think about it. It would be very hard for me here to mention one specific. But whenever you say introduction to dynamical systems, like Devaney has some of them. It has many pictures. It's very interesting. So it has relations. I think the books of Devaney have relations to fractals. So it's very nice to see the fractals, and it's a good motivation for studying dynamical systems.
Very good, thank you. A question now from Zheng Yang. Are there many strictly proven theorems about dynamical systems, or are there mainly numerical results?
Oh, both. Both. There are, I mean, I only do proofs. I don't know how to program. But there are many people who try to give predictions based on numerical things. There is a field of mathematics which actually started being very pure. It's called KAM theory, due to Kolmogorov, Arnold, and Moser. And it started pure, but people make many experiments based on this. And also, biologists, they have a field which they call complex systems. And complex systems is just it's not just, but it has relations to dynamical systems. So you can see that as like applied dynamical systems. And what they do is they do many things numerically.
Thank you. We have time for one more question from Ravindra. How much does the Sharkovsky theorem contribute to the understanding of the behavior of a system as time goes?
Okay, so well, first of all, it's a beautiful result. It demands almost nothing, so it's very interesting. I'm going to take the chance to say about the history of it. It was published by Sharkovsky in Russian in 1964, I think, and it was not discovered by the Western civilization. By that time, we were at the Cold War. It was published in Russian, so people did not know about it. A few years later, York and Clark, Lee and York, they proved a result which was only the second part of it. point of period 3 implies points of all periods. And it became automatically very famous. And after it became very famous, I think that people in the Eastern community said, wait, there is this theorem of Sharkovsky, which was already proved 7 years ago, which tells much more about the periodic points than this recent one. So people rediscovered Sharkovsky. And well, it's influential in the sense that it tells you that in dimension 1, you have a complete solution, and it's actually sufficient and necessary conditions for the appearance of periodic points for continuous functions. So Sharkovsky also gave examples that, for instance, an example of a map that has points of all periods from 5 onwards, but no period 3. So it showed that his order is actually the better you can get, is optimal in the sense, necessary and sufficient. So in some sense, it closed the deal, the field in dimension 1. So it was very influential in this regard.
Thank you very much, and thank you again for these, well, incredibly interesting answers, and thank you all for all of your incredibly interesting questions, which led to these interesting answers. And let's thank Yuri again for this very nice talk.